coefficient size of Nullstellensatz proves the Pigeonhole principle. And this is joint work with Aaron. Okay, so for this talk, I'll take 0 to be false, 1 to be true. So here I'll think monomials to be a product of variables and their negations. So as you likely already know, given a given a set of axioms AI, Nullstellensatz proof of infeasibility. Is an equality 1 is the sum over I of pi times pi. Okay, here like all the the polynomial is all b to be 0. Right, and this proves they're infeasible as like if all the a was 0, then we have 1 equals 0. So now often in proof complexity, we'll look at the size and degree. So here, so today we'll look at the total coefficient size. So we'll look at the sum of the coefficients of the monomials in the PI. Okay, so why analyze total coefficient size? So That's it. One is that there is a natural linear program corresponding to total size.
What happens if it's negative coefficient?
Absolutely.
Sorry, some of the magnitudes. Some of the magnitudes of the coefficients. And second, so total coefficient size gives lower bound it gives lower bounds on unary proofs. And proofs with bounded coefficients. So as as Robert talked about, so unary Nullstellensatz is connected to reversible resolution with terminals. And unary Sherali-Adams is sorry, the intersection of unary Nullstellensatz and resolution. That's that. I almost forgot that.
So Aaron, we should think about being over R because we're measuring.
Yes, and here,
Big characteristic
here
zero.
we are. Oh yes, so here we are working over R. Thank you for the reminder, and yes, but if at any point you have questions, feel free to interrupt. Okay, so the linear program is as follows. So given an axiom A, we define a weakening W of A to be R times A for some polynomial R, and then the primal program is going to be to minimize the sum over W of the coefficient, the magnitude of the coefficient W, subject to the constraint that for all x, the sum over x of CW times W of x is equal to 1. And then, so here, we'll analyze this with the dual program, which is to
Sorry, the primal program doesn't seem at the moment. Oh, okay, I see. W up there is the weakening. Okay. Yes, okay, fine. W is a weakening of A, right?
yes, that's
Yeah.
and then the dual program is to minimize the sum over x, maximize the sum over x, mu of x, where mu is a measure on assignments. It is a measure on assignments. Such that for all weakenings W, the sum over x mu x times Wx, this magnitude is at most 1.
So here's what you have one axiom here, but obviously some of these, you've got collections. How do these extend to? How does this?
So here, like, I want to take the collection of like any axiom times any maneuver.
Okay, so this is over, so W is over all weakenings of all axioms, okay.
Yes, that's exactly right. And then
And from what set from what set X is?
so x is all possible assignments to the values.
Boolean.
Yes, so here, like, we'll be working over Boolean. And then for mutuality, so if we have both this measure and a proof such that the sum over given the measure mu and the proof, we'll have that the sum the sum over x if we sum this equation over x, so we'll have that the multiplying this equation by mu of x and summing over x, we'll have this. And then and then here this I have to go around. Okay, that, oh, yeah, that's right, the sum over x of w x times mu of x is bounded in magnitude by one, so this is going to be upper bounded by the sum over w of tw, which is the total coefficient size. Okay, so the okay, I'm not doing so well on time. But here's an example of if we had the simple axioms 1 minus x1, 1 minus x equals 0, 1 minus x2 equals 0, and x1 times x2 equals 0, then we'd have these weakenings. The parallel program will look as follows. And then the minimum total coefficient size is 3, as some of these three equations already give a lower bound of 3. And this would be a dual solution. So now we'll analyze this for the Pigeonhole principle. We're here with the so here we'll take it to be like n plus 1 pigeons to n holes in order to make the numbers easier. With the usual so we'll have like xij equals 1 if pigeon I is mapped to hole j. And then we have usual axioms xi1j, xi2j equals 0 if I1 is not equal to I2. So the whole axioms, and then for all I, the product over j of 1 minus xij equals 0. So
What is mu? You said it's measure on.
It's a measure on assignments. So here, like, actually, I'll illustrate it with an example momentarily.
What is
So
it?
here, and so we'll restrict our attention to assignments mapping each pigeon to exactly 1 hole. So our lower bound applies to the functional pigeonhole principle. And then the idea says, it's similar to the Sherali-Adams load, the degree lower bound for the Pigeonhole principle is that if we're looking at less than all the pigeons, then we'll pretend that all that they are matched uniformly at random to different holes. And I'll elaborate on what that means in this setting now.
Does U have some properties that it needs to perform?
So in particular, we'll take the following the following to the measure. So let's given a subset of pigeons, we'll let JS of X be 1 if X maps all the pigeons in S to different holes and 0 otherwise. Yes.
Does the lower bound also apply if you have dual variables?
Oh yeah, in fact, like, we define monomials to have like xi and 1 minus xi, so say yes, we have dual variables here. Okay, so we take mu of x to be the sum over subsets S not equal to all the pigeons of CS times JS for this coefficient. And then but for example, if we have like 3 pigeons in 2 holes, then for assignment mapping all 3 pigeons to 1 hole, we get a coefficient of -1. And if we map 2 pigeons to 1 hole and 1 pigeon to a 3rd hole, then we get a coefficient of 1. And then the sum over x and mu x in this case turns out is 4. For 4 holes and 3 pigeons, the coefficients are a little bit more complicated. Turns out the sum of x, mu x is going to be 18. For these 2 examples, it turns out that like for all weakenings, the sum over x of mu x times wx has magnitude at most 1, but this won't be true for a higher n. Let's see. Are there any questions that you'd like to ask? You'd like to ask about this measure?
So
Did you find it?
it's, I mean, it's obviously sort of some fraction of maps or something like that, but the signing is kind of, yeah.
So I'll describe the key property. I realized that I'd forgotten to actually state our results. That was 1 second. Let me quickly state our results. And then I'll describe the key property that we use, and then I'll be essentially out of time. So any Nullstellensatz proof of the Pigeonhole principle has size omega and n to the 3/4 2 over the square root of e to the n. And we also give an upper bound that there is a proof with total coefficient size at most to the 5 times n plus 1. Let's see. So actually, I should also remark that this work is similar to my work with Killian and Susanna. A difference is that Then we considered a Sherali-Adams and really use with the fact that the input is random. Here. There's no random input. Instead, we're considering the very symmetric Pigeonhole principle, and we're directly using combinatorics. So the key property.
What is S?
It's subset of pigeons.
As a subset of pigeons. So the key property is that for any function f, which doesn't depend on some pigeon I. The expected value over time is matching like to exactly one whole. Mu of x times f of x is equal to the expected value this expected value. So that says that if f doesn't depend on some pigeon I, then we pretend that we have the uniform distribution. The other opinions are matched uniformly at random to the other holes.
Aaron, you have 5 more minutes.
Let's see. And actually, I have to go. Get my taxi. Okay, yes, so here.
What is the J speakers?
Chase this function of the mapping pigeons from the middle board.
Very efficient. Oh, okay. Oh, here.
And oh yeah, the idea here is just that CS and J for all S except S equals like all the pigeons except for I, the CS times JS cancels with CS union I times J S union I. So let's see. So quickly say the following. So using this, it turns out we can use it so that we can restrict to weakenings where each pigeon can only go to half of the holes. So it turns out that this argument, this argument doesn't give the lower bound, but they can be patched. But yeah, unfortunately, I'm out of time, so I think I'll just say some. I think I'll just say some moving problems. So one is what total coefficients size bound can we show for the total ordering principle? What happens if we have more pigeons? As it turns out, the current proof, like what works when use a trick which works when we have exactly one more pigeon than whole. And then the last as the lawyer also asked, would total coefficients lower bounds for SOS imply resolution lower?
Okay, thank you very much.
Thank you.